E less than V naught. So you have an incident wave e to the I kx, incident, and a reflected wave that you have e to the minus I kx, remember, minus the other phase and e to the 2I delta of E. So this is the incident wave, and this is the reflected wave. They correspond to your A e to the ikx plus B e to the minus ikx. Remember, when the energy was less than V naught, the ratio of B over A was minus e to the 2I delta. And since I take A equals to 1, you get this thing. So suppose I construct a psi incident of x less than 0 and t as a sum 0 to infinity dk f of k e to the I kx e to the minus I e t over h bar. Whew. So I superpose the incident thing here. Then the reflected one should be superimposed too. And would be 0 to infinity, a minus in front, because there's a minus, dk f of k e to the minus I kx e to the 2I delta of E e to the minus I e t over h bar. Whew. That's the reflected wave superimposed. So now you've constructed everything. Here, the reflected wave is more interesting than the transmitted wave, because there's no real big transmitted wave. It just whistles out. But the reflected thing is interesting. If you're doing the experiment, you send in a particle, you want to see what you get back. That's going to tell you what kind of potential it encountered. So let's do the stationary phase for this one, for the reflected. Let's see how it moves. We know how the incident moves. The incident moves with x equals, we've done it there, hk naught over mt. But how about this one? Well, this one you would have to do ddk of minus kx plus 2 delta of E minus et over h bar, all that at k naught equals 0. And you probably remember that this thing was in your midterm, in your first test. You had this wave, and you had to analyze what did stationary phase do. And it does that. So what do you get? Well, when you take the derivative, you have to take the derivative of delta with respect to energy. That's delta prime. And then the derivative of energy with respect to t. Let me save you a little time. The answer is minus h bar k naught over m t minus 2h bar delta prime of E. OK. That's what you get. That's how this packet moves. And what does it do, really? Remember, this is defined for x less than 0. So this is valid. Forget about this little term here. This is valid for t positive. For t positive, you're going to get this to satisfy. So this is a big wave packet for t positive. It's a reflected wave. That's what you would expect. This is the reflected. Now, if this factor was not here, it is as if, well, the incoming packet hit the origin at t equals 0, and this would be perfect bouncing, in which the packet gets reflected, and at t equals 0, it starts to move to the left, and as t increases, it moves more and more to the left. You see it there. because x must be negative. But if there is this term, it really doesn't start to move to the left until t is bigger than that, so that x is negative. So only at t equal to this amount of time, the packet reflects. So there's a delay, and the delay is 2h bar delta prime of E. So this is a technology people use in scattering theory to figure out what kind of potential you have, figure out how much things get delayed from the bouncing. Now this derivative, we plotted it there, delta prime of E. You get a big delay for low energy, for energies near V0, and in the middle it's not so big.